So as always, welcome everyone to the meeting. And this week has been sort of a week to consolidate a lot of the implementation on different algorithms and hopefully apply them to Atari games. So in this week in particular, I was focusing my effort of trying to apply PPO to Atari games and see how well it'll perform. Um, well, the journey has been very difficult at times. And there's some very interesting details that I would like to share with you. In particular, I think one of the most interesting things to first look at is probably uh, different termination conditions of the environment, and uh, that could mean very different things for different algorithms, especially for A2C. So I prepared a script, and let me kind of show you. And how many of you have heard of the vector env by OpenAI baselines?
Probably say pretty much everyone.
Pretty much everyone? Okay.
Yeah, we heard it from your last talk, I think.
Okay. Nice. Yeah. So vector env, for if in case anyone wasn't familiar with it, it's an environment wrapper that allows you to run multiple environments at once. And here is the toy environment that I prepared. Essentially, let me run it. So essentially, at each time step, it produces the observation corresponding to the time step. So for example, at time step 0, it'll produce observation 0. At time step 1, it'll produce 1. Time step 2, observation 2, etc. And we consider the environment will always end after 10 time steps. And this is what we consider as by the way, is the text readable, or should I try to enlarge it a little bit?
Little bit, please.
Yeah, how does it look now?
That's better, I think.
More legible? Let me see if I can do the same. Right, sorry, I could not do the same for the right-hand side. I'll just do it for the left-hand side, and if I want to show you what happens on the right-hand side, I'll just zoom in. So essentially here I have a test env, and then its observation look like this for a given episode. If I just run it, it runs for, let's say, 2 episodes, and each episode takes 10 times, 11 time steps to finish from 0, and at each time step, it outputs the observation that correspond to the time steps number. So this is the first kind of termination condition in a given environment that is considered as true done. As an example, the true down of breakout games in Atari 2600 comes when you lose all of your lives. The second kind is what's known as time limit done. And that's what OpenAI Gym does to a lot of environments. For example, like Carpool. Carpool always finishes within 200 time steps, even though. So if you consider the carpool, right, the true termination condition should be when the carpool sort of fall over to one side. That's considered as a true termination condition. However, in practice, the environment always finishes at time step 200 because you really shouldn't have it to go on forever. So that's and they achieve this by using this time limit wrapper. And if you look at how it's being registered, it sort of looks like this. You register with an ID, and then you say the max episode length equal to 200. In the case of our test environment, we just set the max episode steps to be 8. So as a result, we ran it for 2 episodes. And then if you see what's on the right, by the way, can everyone read what's on the right?
Yes.
Okay. So as you can see, what's going on the right, the episode for the two episode, the observation goes from 0 to 8, right? Means the environment is not truly done, right? Does that make sense for the time
So
limit
far,
done?
so good.
Okay,
Yes.
okay, right. So this is how the time limit done. Okay, so these two things are very intuitive. Makes a lot of sense. However, in a way, this is when things gets tricky with the vector end because it does some very interesting assumptions. So over here, I create a vector env and I ran for 3 episodes. And then this is the observation. You go from 0. By the way, for the vector env, I set end step equal to 5, which means the environment always goes for 5 time steps. So to sum up, right now we have the true done comes at time step 10. We have time limit that hits at 8, and we have the end steps equal to 5. So by using the vector env for the episode 0, this is its observation: 0, 1, 2, 3, 4. And then this is observation at the second episode: 5, 6, 7, 0, 1. So this is when things gets interesting, right? The episode finishes at 7 because uh, the observation of 8 is considered as a terminal episode, therefore it's not presented in the vector environment. It's sort of hidden in the info section. And then instead of this being the observation of 8, this is the observation of a new episode. And sorry, this is the observation of the environment that has passed the time limit. Therefore, you see 0 instead of seeing 8 over here. And you have 0, 1, 2, 3, 4, 5, 6 again. And I think it's important to realize this difference because it makes the assumption that your observation, in a sense, reaches it's possible for your observation to reach the end of episode in the middle, and then you start a new you sorry, your game is sort of finished in the middle of your episode and is starting fresh in the middle of your episode. Does everyone see that?
So far, so good.
Yeah. So that's how OpenAI baselines handle games like Atari. So there's a motivation for it, right? Because for Atari, theoretically, your time steps could go on forever, right? If you, let's say, just say pawn and then you never fire that ball, the game could go on forever. That's why, first of all, there's a time limit. Instead of the true done condition being forever, the time limit of Atari is 400,000 time steps. However, 400 time steps is an obscenely, it's an absurdly large number of time steps. And if you were to train, let's say, A2C or PPO based on that particular episode, it's way too much observations in an episode. And as a result, OpenAI Baseline's PPO, or for A2C for that matter, they makes this assumption that you're using this sort of vector env, and then you have limited end steps. So for example, for Atari games, the end step is set to 128. So instead of running the whole game of Atari, it sort of consider each chunks of observation as the episode for PPO and A2C. Okay, so hopefully that makes sense. And I find that to be very interesting because it kind of changes the way how you would think about these episodes and the game settings. So okay, so that's just some distinctions that I want to make. And basically, I did a lot of experiments. I have a little notebook, just kind of show you some of the experiments that I tried. But essentially, even though we spent so much effort even though Rosalind and I spend so much effort on PPO, there are still at times that I find new things. So, for example, the layer initialization is a little different than we implemented, which we kind of talked about in the paper. We really should have implemented initialize it in a more correct way, but it's hard. It's very hard to realize these differences. So, in particular, their code is hidden sort of in many different files. So, take layer initialization as an example. They use orthogonal initialization with scale numpy square root of 2 for weight and the constant zero, constant initializer of 0 for biases. So, for example, the way how they built the convolutional neural network for Atari, what they do is you see this in its scale is numpy square root of 2 for all of the hidden layers. However, you thought this is it, right? No. In the different files, how they actually build a policy, they in particular see this line stuff.pd type probability distribution type probability distribution from the latent layer sets the init scale equal to 0.01. That means for all of the hidden layers, the initialization scale for the orthogonal initialization is all square root of 2. However, for the output layer of the policy, excuse me, they use the initialization scale of 0.01. But for the value initialization, they initialize it with the scale of 1. So that's a layer initialization. A lot of details to sort of notice in the PPO's implementation. And secondly, the trainer is also initialized with epsilon with 1 e minus 5. This is in a way not so much of a difference to be taken care of, but it could matter. And also, this is something advantages normalization. Interestingly, the advantage normalization happens at the mini batch level, which may and according to our experiments, it could make a huge difference. So over here, okay, I need to zoom out a little bit. Over here, this is the episode reward. And if you look at the light blue line, that's the advantage normalization of the whole batch of data. And then no advantages normalization is a gray line. It kind of performs okay. But if you normalize the advantages on the mini batch, it actually performs better. And this is something that I realized that one of the popular library from this person called iPositrov. This is one of the most famous PyTorch implementation of PPO. It seems that they were doing the advantages normalization at the whole batch level, which would have been a discrepancy from the OpenAI baselines implementation. So, for example, if you go to algorithm, PPO, actually, my bad. They implemented correctly, I think. Wait, is it? Yeah, they did, right? So over here, this is when mini batch happens, but the advantages is already normalized before doing the sampling process, before creating the mini batches, and that is incorrect because, well, at least not the same as OpenAI Baselines implementation. If you read about OpenAI Baselines implementation, what you would found is that so they get a whole batch from the runner, and then over here, they train the model based on, so they get the mini batches over here. This is the M binds. It's a mini batch. and then they take the mini batch from the observation returns max, etc., and then they pass into the model, and then the model does the advantages normalization, right? Wait, where is... Yeah, so over here, right, the train takes in the advantages, but this advantage is already the mini batch version. This is the train method that is being called here. And over here, the slices are the mini batch. So yeah, so that's one major discrepancy that happens between the OpenAI baseline implementation and PPO and the and icosutral eco-strikeoff implementation of PPO. But yeah, overall, there's just a lot of implementation details that needs to be paid attention to. And initially, I wasn't exactly able to reproduce the OpenAI's baseline's results. This is OpenAI baseline's results. The curve looks unbelievably smooth. Um, Obviously, that is very well tuned, but everything just kind of looks smooth. There's no values that are sort of act as a spike. But initially, in my experiments, there was a lot of spikes, and after 10 million type steps, I was only able to get about 150 reward instead of 400, which is a reward obtained by OpenAI baselines. And one thing that I noticed in particular is, so all of the metrics, the approximate KL, entropy, policy loss, look very similar to the shape that the OpenAI baselines library exhibits. So for example, the entropy reached down to about 0.8 at the end. Mine entropy was a little is 0.6. That's not a major discrepancy, but value loss is a major discrepancy. Mine reaches about 5 for the value loss, but for the OpenAI baseline library, it never exceeds 1, for example. And as a result, I kind of tried to reproduce the results using the Iko Strikeoff's library of PPO, and he was able to achieve very incredible results as well. So that would be the blue line over here. Very smooth line, achieves very good results. Let me comment out this first.
You say smooth, but I think it's actually quite manually smoothed, right?
No, I actually logged the raw rewards. So in particular,
you apply smoothing with TensorFlow.
yeah, but if you, even without the smoothing, it looks like this, right? So that is, yeah, that is not a huge problem. But there's no spikes in the beginning, especially. But that's sort of a huge difference from my implementation. And I also did a couple run using logged using weight and biases. And because of the vector env, what you would found is that there's actually multiple videos of the agent playing. Sort of handled by the weight and biases monitor gem equal to true automatically. So it's kind of beautiful in its way. But anyway, the results isn't that good. So the short version of the story is I figured out, kind of. So in particular, this is my implementation results. And this is the same PPO implementation that sort of results in this, that only achieves 70 rewards. The only difference is that I, instead of creating the environment using my own wrappers and stuff, I just called the make vector env commands from Iko Strikeoff's library, and it works perfectly. So I guess that's kind of a consider as a mystery solved. And also the value loss, matches more closely to the trend that is being exhibited in the OpenAI baselines library. In particular, there's no spikes that goes up to 5 or something. It remains under 1. So for my next step, I would only have to just figure out, first of all, how do they log the rewards, which I believe really is the same, but also how do they handle the pre-processing. I think they use some vector, they manually implemented the stack frame. So it means stack 4 frames of the Atari observations so that the agent can, for example, infer the velocity of the ball moving and what is its direction. But everything I really think those should be equivalent, but the performance difference tells me otherwise. So that's something that I'll be spending time to investigate over the next week or something. But I think by using this, it would work for PPO and for A2C as well. So kind of spend a lot of time on it because I really want this to work because it's kind of related to my research. And if I can have a really powerful, correct implementation of PPO, I think it will help with my research a lot. And that's why I was spending a lot of time on it. And eventually it kind of works. I just have to figure out what's different in the environment. So that's kind of my findings so far. Any questions?
Regarding the toy example you presented us,
The poor example, you mean this?
no, in the spider
Okay.
editor, there is a
the toy example.
Where
right.
The first observation is 6, and the next 7, and then it resets to the real new episode.
Yes, to 1, right?
Which was the cosec. Is it a time limit who does this?
Yes. So the time limit. So over here, right? 5, 6, 7, and you really should go to 8, right? So here's something that I can do, right? Instead of doing this, I'll print info. I'll just say print info. And then just hit run. And what you have found is this, right? Over here, you have 5, 6, 7, and then this is where what you're looking at. When it happens to reach the time limit, the time limit truncated is equal to true, and also there's this terminal observation of 8, which should be here, but it's replaced by the vector end automatically, and you have to retrieve it by using the terminal condition, terminal observation.
That's OpenAI baselines backend, right?
Yes. There is, however, a vector and a wrapper also provided by OpenAI Gym, but in OpenAI Gym, I don't think they do not give you this terminal observation, which I think is bad because, in a way, I almost feel like the way they implemented the way they implemented the advantages calculation is incorrect because even though the environment is done by the time limit, you really should bootstrap your value based on this terminal observation, but they don't. They only bootstrap the value if it sort of ends like this: ends with 4, ends with 1, ends with 6, which is reasonable. But I think technically you should bootstrap values for if you reach the terminal observation and the time limit is true. And that is also not handled correctly by the, in a way, sort of, by the ICO strikeoffs library. So I think they're actually trying to do that, which is very good. But I don't think they handle it exactly correctly. So they have somewhere over here has a time limit mask. So over here, right? Let's see if we can zoom it in. over here, they're saying essentially, oh shoot. Okay, you can go back to normal. Okay, I'll just zoom in. So they're essentially saying if done, and then the maximum episode steps is equal to the elapsed steps, then it's a bad transition. But that is not always true. It is possible that your real task ends at exactly the time step that you reach the time limit. Does that make sense?
So a bad transition is when the time limit, the fixed time limit is exceeded.
Yeah, so checks whether done was caused by my time limits or not, right?
Interesting.
Yeah, so in particular, this is not always true. It is possible for your environment to terminate at exactly the time step that the time limit kicks in. So it's still very, very high quality implementation. But I think technically it's not exactly implemented correctly. So just just little things. So that happens when you bootstrap the values, right? So over here, your computer returns, you get the value. If you use proper time limits, that's when the bad masks kicks in. But as we discussed, as I showed how they calculate the bad mask, this is not always true. The bad mask is not always correct. And below is how OpenAI Baselines library calculates the general gradient estimation. So in particular, they don't do the bad mask at all, which may or may not be a bad thing, right? So it depends on if your carpal finishes at 200 time steps, is the terminal reward the value of the terminal state, or should it be just zero? So that would be sort of an interesting question to answer. But right now, I don't have answers to that. And also, I didn't exactly enjoy the way they write up the storage. It's really long, first of all. And also, I think it's kind of confusing to read. Like, there is this method that is really confusing. It says after updates, and then you first observation copy the last observation, you mask copy the last mask. In a way, it doesn't really make much sense to you as what it's trying to do. It makes sense to me now because the reason why they needed to do this is because when they pass, if they want the agents to execute an action, they always pass the first observation in their rollouts. So which is always this self-DAW observation 0. That's why they needed to do this. But I think, in fact, OpenAI Baselines library has a cleaner implementation for that aspect. There's no implementation of rollouts engine. If anything, it looks more like this. By the way, this is the main three that produces these results, which is very good. Produces a gray line, which is very good. So in particular, for my implementation, I just have the observations and then calculate the GAE. There's no rollouts engines. Yeah, for me, that thing is a little bit strange, um, but yeah, I'm just kind of glad that I got it working, and then I just need to figure out what's the environment difference. So, any questions or comments?
Okay, also regarding the VecAmp implementation, since we have like a parallel environments, right? And the agent, so at each time step, the agent receives actually not one observation, but let's say we have 16 environment, like a batch of 16 current observations.
Yes.
And it outputs like 16 corresponding actions.
Yes.
Now, depending on the environments, probably some will finish earlier, some later, and then, well, the agent is basically multitasking. I don't know if it's if it
Sure.
makes any sense. Okay. And probably because there is like this discrepancy in the trajectory it's generated, I think that's why they're doing something like the rollout storage to keep the logic in the transitions. Or did you find it to be the kind of a problem? How do you manage such a, I don't know,
like how do you manage the termination condition?
No, how do you store the data in the buffer to maintain the logic in the transitions?
Right. So
Actually, I don't think we need a transition, right? They don't necessarily need to be in order, so does it mean that we can store it?
so this is the logic, right? You have the storage instead of being a storage class that has inserts after update. Um, this is just it. At each update, you create a bunch of storage, and then you execute them, calculate advantage. Done.
I see.
Right. So according to their implementation, over here would be some sort of insert, and then after the advantage is calculated, there needs to be like a rollouts after update. In addition, when you insert the observation, you also need to recalculate the header of the rollouts. So that specifically corresponds to this sentence, this code right here. Yeah, I don't know. I just personally find it to be more distracting, and it's more difficult to debug because the computational process is within the function, and then if you want to examine the computational process, it's more difficult. So, for example, if I want to see what the delta is, this is very difficult to. It's not very difficult. It's just it's time consuming. What I would have to do is to sort of rewrite this, replace all the self with the rollouts and stuff, and I need to also somehow get the next value, which is calculated internally here somewhere. It makes debugging more difficult, but it can be done. But if you're just doing it so transparently, like it's been done over here, what you can do is just print out the delta, and that's it. Right.
Interesting.
So that's also the whole motivation behind no function wrapping as much as possible, because it makes the inspection so easy. I can see what the observation is by just printing it out. And this is also the thing that Python allows you to do, because it's a dynamic language and you can debug on the fly. And for me, it doesn't make a lot of sense to always, add some print statement in the middle of some function and then always execute this code from scratch. It's much easier to run the function, run the program, and just Control C out of it. And then if I want to see, I can just say check the advantage. Oh, what is the last 20 advantage? What is the first 20 advantage? I can do that. So for me, debugging is a lot easier. And also there seems to be a performance gain by using the wrapper. I think it has to do something with the tensor conversion sort of stuff. So in particular, if I use a relative time step, let's see. So his implementation is very good. Mine took about 2 hours, but by using the original wrapper that I had, I think it's way longer than that, right? So mine original one took about 8 hours. Wow. My implementation was bad. So this is all 10 million time steps, and his implementation. So I think the most difference probably comes from how you sample the data. He uses this batch sampler thing. So I don't know if I can. Yeah, it's somewhere over here, right? It's batch sampler and subset random sampler. I think that may help with the performance. I don't know, but it could, because probably PyTorch has some magic in there. But this is something that I do not want to optimize over, because I think it complicates the code, and I think the performance gain is not that much worth it. But I definitely think their environment, how they convert the tensors, is worth studying, because it speeds up the program from 8 hours to 2.5 hours. So I think that's very good. It's all about the bottleneck, right? Right. So in addition, I'll also share some details. I don't know if I can find the experiments in the beginning, but layer initialization initially makes a huge difference to me. Let's see if I can. Yeah. So let's see if I can find a longer version. Right. So this is sorry, not layer initialization, but rather the inputs normalized to the range of 0 to 1. So it's specifically the scale operation that scales the pixels from 0 to 255 to just 0 to 1, and that makes a huge difference. So initially, I didn't do that, and the agent wasn't learning anything at all. It just sort of stuck here. But then, as soon as I I add that normalization, which also again is done by OpenAI baselines. Then the agent was quickly able to learn to say, um, at least learn something, as shown, sort of similar to this. The agent is at least able to learn something, but not as good as the main three over here, which should be additionally an additional detail that I should add. Scale from 255 to 0 to 1 matters. I plan to write a blog post on all of the implementation details on PPO. In particular, so in the paper that implementation matters, they only list out the code level optimizations, but in actuality, I think some of the things, even though they're not technically implementations, code level implementations, like for example, the mini batch update is mentioned in the original paper, but mini batch also matters, and also the scales matters for example, Atari domains. So I think if you sum up all of the implementation details, I think the quantity probably goes to 20 or something. So I feel like that would be just serve as a checklist for your PPO implementation. But anyway.
Nice. So what's the batch size they're using for Atari environments for PPO?
I think by default, the batch size is actually quite large. It's 128 times how many cores you have. So in my computer initially, by using OpenAI baselines, it's 128 times 24, which is a huge number. But by using Iko Strykov's library, he sets the default number of environment to be 8, I believe.
So the what do you call it? The epoch data is 128 times number of environments.
Yes, exactly.
Your results, are there using any form of KLE variant?
No. This is just a really, which by the way, I'm just trying to reproduce the OpenAI baselines results as much as I can. However, KLE is very interesting. Let me see if I can find that example. Probably not. Yes. Okay. So if I remember correctly, this is the KLE example. And this is done without using the scale, the observation from 0 to 255 to 0 to 1. And then if you compare it with, let's say, one of the other examples. Need to find an example that runs for quite a long time. Come on. Right. Okay. This is probably good. So over here, right, you see the gray line in the bottom? This is without KLE. And you know there's KLE because you see the spikes. You see the PG stop iteration, right? And then the reason why the bottom one performs so poorly is because in this case, it's not KL explosion, it's KL degeneration. The KL becomes 0. So there's some policy updates. And actually, sorry, there is KL explosion. In particular, I think in the beginning, it was so huge, right? Yeah, but I remember in the beginning, I actually checked the debugging message. In the beginning, the first update, the approximate KL is actually 5.
Well, and it's understandable since the network was just initialized.
Oh, yes, indeed, because it's initialized according to orthogonal initialization and the inputs is so huge, like 255, and then the KL divergence just blows up, and then the performance just degrade like that. That's why it wasn't able to learn anything. But then if you add early stopping optimizations, then you control the KL explosion, then it's able to learn something at least.
Interesting.
Yeah, it is interesting. Yeah.
But I guess we should probably tidy up the backend and all that stuff before focusing on
the what?
The diverse environment managing, I guess. The environment related tricks.
Right. Right. So anyway, last details to sort of completely reproduce OpenAI baseline's results. What I also did was to use the same value head and share parameters between the policy and the value function, and that could be done easily. It's basically this. You initialize the network, and then you create an actor that based on these. What are some additional details? Oh, right. So another thing that I did is to do the losses exactly the way that OpenAI baselines do the losses instead of spinning up. So for those of you who didn't know, OpenAI baselines actually do, OpenAI spin up actually do the losses of the policy a little differently. The person, John Akiem or something, yeah, he presented a proof of his approach of doing a policy loss is equivalent, which I believe, but for a complete reproduction, I just want to revert back to how OpenAI baselines do the updates. And it actually makes a difference, but might not be it might not due to the difference between the policy calculation, but rather let me see if I can show you first. So for example, OpenAI spin up, they clip the advantage and multiply that by the ratio. However, in OpenAI baselines, it's not the same. They're having two policy laws and take the minimum of them. They're using minus and minus, so that's why the max over here. But yeah, I just kind of revert back. But fundamentally, the how PPO from spin up and baselines are different is how they calculate the loss. And this is one of the really huge difference. In baselines, they calculate the loss by using this sort of regime. Policy loss minus the entropy plus the value loss times the value coefficient. And the entropy is multiplied by the entropy coefficient. But in OpenAI SpinUp, they implement the value loss using a different optimizer. So in other words, the value coefficient times the value loss is not sort of considered, which may or may not have an impact on the performance. I think that's pretty much it for all I have. Yeah, so for the next week, I'll be trying to make this script more readable. Right now, it's kind of hacky, a lot of things. But I'll try to make that more readable and then upload it to the repo, as well as starting trying to apply A2C as well. And I think we would have enough for the 0.30 release because we have PPO, A2C, C51 DQN working for Atari games, and we also have results for the continuous action domains. And another thing I would say is to rename the files. For example, I have PPO2 to denote PPO implementation with all the code level optimizations. But maybe I should change it to just PPO and rename my PPO.py to something like PPO_naive.py because it's not augmented with all of the code level implementations, or PPO simple. So that I guess people wouldn't be confused by why is there a PPO2? What does that mean? But yeah, that's sort of what I have. Any questions or comments?
Great job, as always.
Thank you.
But it's so messy.
You're
and those vec and all that stuff.
Yeah. The vector env, I think it's really important to understand what it's doing.
What about the DeepMind? Do they also have similar tricks?
At least I wasn't able to reproduce the Atari results. I don't know if they applied any additional tricks. And it seems that they didn't. That seems to be my observation. Including the Impala paper, they don't seem to do all of these things. Impala just seems to be working quite well right off the bat. And that's actually interesting, right? Do they do the scaling down from 255 to 1 to 0? So Torch Beast. And I go to core, environment. Yeah, they don't. I'm not sure. I have to look into it, but it's possible that they didn't do it. So in a way, Impala would be a better algorithm. And actually, Impala doesn't have the vector env because they just sort of execute multiple environments by using the multiprocessing library. So in a way, it's more straightforward. Actually enables.
Are they using MPI?
I think so. If you and their code is also very simple to read. Surprisingly, this is the only, as far as I know, the only deep reinforcement learning library that is easy to read. I mean, it's still quite long, 600 files or so. But yeah, they're using NP, simple queue or stuff. They're essentially having a bunch of processes to take things from the queue and then execute it, which makes it very fast. And you don't have to worry about the low-level things like vector env, and it's performing very well. And from my research, I actually probably should try to implement it. And there's no layer initialization tricks and stuff like that, right? So for example, if you go to here, There's probably a model somewhere. Yeah, where is the model? Oh, it's over here? All right, Atari Net, right? Did they do the initialization? No, right? They didn't. It's just simple. It's just a convolutional neural network and stuff. Oh, actually, it did. You see the 255, so it matters for them too. But they didn't use a orthogonal initialization. What is this? Tilde.
That's the first time I see it in Python.
Yeah, that's my first time too. That's so weird. What does that even mean? Tilde 1?
It says reverse operator.
That's strange. I wish they hadn't done it, but okay. Right. But yeah, if I were to do this, I'll be implementing it and try to incorporate the invalid action masking in Impala as well. But anyway, any questions or comments?
It's really interesting.
Thanks. Where is the video? Right over here. Well, if we don't have any additional questions, then I think we should probably call it a day. Thank you, everyone, for joining. It's very interesting. Hope you have a good weekend.
Thank you. Yeah, thank you. Have a nice weekend. Thank you.
Thanks. I'll see you guys.
See you.
Bye.